Hello, my name is Kyle Rojek, and this is part 2 of exam 2. So in this part of the exam, we'll be generating 100 pseudo data points between these given parameters, and then we'll be applying a 10% experimental error to the Sherwood's number, and then we'll be using this correlation and applying linear regression and the Penrose pseudo inverse to hopefully obtain these three coefficients. Next, we'll be using the sum square error and then minimizing the sum square error to hopefully achieve those coefficients again. And lastly, we will plot all of our data points into a 3D model. So to start out, let's import all of our libraries. First, starting out with NumPy, and then subplots, so we are able to make our subplots. And then our graph objects, so we can make our scatter plot. And then plotly.io. Then lastly, our minimize function, so we're able to minimize our sum square error. So next we'll be generating our 100 data points. So starting out with Reynolds number, we want 100 random uniform data points. Those are between our parameters. It's 100 data points. Nope. And then next is Schmidt's number. Between their respective parameters with 100 data points. And next we'll be inputting our 10% experimental error to Sherwood's number. And those will be normally distributed. With the scale being 10% applied to Sherwood's number. So here we have all of our generated data with the experimental error of 10%. And next we'll just plot all of these points. So we want to make our figure. Then we'll be inputting all of this stuff into a scatter plot that is 3D with our x variable being Reynolds number, our y being Schmidt, and z being Sherwood. And that will have the mode of that will be equal to markers, because we don't want to plot these as lines. And then we'll make a marker size of 3. And then a marker color of the Sherwood. I hope that's right, but I guess we will find out shortly. Alright, next we want to update the layouts of our graph. And for that, we'll use a width of 800, a height of 800, and then the scene to the dictionary, we'll be naming it. So we'll label X as Reynolds, nope, X-axis as Reynolds, our Y-axis being Schmidt, and our Z being Sherwood. So let's see if that worked. Of course it didn't. Alright, let's do some oh, I see it. That's what we messed up. Alright, and here's our normally distributed data. Alright, next we want to do linear regression on our correlation up here. And to do that, we will take the natural log across the whole equation. So we'll show that in terms of A, B, and C. So now that this equation is in the linear form, we are going to make a design matrix. And to do that, we are going to stack up all of our values next to each other with a row or a column of ones for our dependent variable, which is the Sherwood number. So to do that, we'll do that in terms of X. And then to make the columns, we do column stack. And then to make the row of ones for Sherwood's number, we do ones like, and then next we input our two independent variables. So the natural log of Reynolds and the natural log of Schmidt's number. And so here's our stacked up array of values. Then next, we're going to want to take the Penrose pseudo-inverse of our sign matrix. And to do that, we take the transpose of the inverse and multiply that by both sides. So do that in terms of W, and then linear algebra dot the inverse of this. And so we have our matrix, the transpose of X multiplied by our matrix, and then multiplied again by the transpose, and then multiplied by our dependent variable, which is now the natural log of Sherwood's number. And so hopefully this gave us our values of parameters. And then to make that first value in the array, we want to take the exponential of the first value. Yep, and that gives us the correct parameters we are looking for. And so next we want to take the sum square error of all of these, and to do that we take the sum of the difference of our dependent variable and then subtract that by our experimental data, and then square all of it. So to do that, we want to define our sum square error in terms of parameters p, and then we want to input the summation, and then our dependent variable, which is the natural log of Sherwood's number, and then subtract that by our experimental data, which is our two independent variables, in terms of the parameters as well. So np dot natural log of a, and no, natural log of our first parameter, which is a, and then add that to our first parameter, which is b, multiplied by the natural log of Reynolds, and then add in our last parameter, c, in turn multiplied by our natural log of our Schmidt's number. Lastly, we want to square all of these, and we want to return this. So then we're going to minimize this sum square error using a function that we imported. in terms of parameters that are close to the ones that we found. So we'll use 0.02, 0.8, and let's say 0.4. And so here we are with our parameters that we are looking for. And that is how you use linear regression and the Penrose pseudo-inverse to find those three vectors of parameters that we are looking for. And then using the sum square error, then minimizing that sum square error to obtain those parameters again. So next we're going to be plotting our model prediction. And by the way, I made a wording error for the sum square error. This is actually our experimental data minus our model prediction, not the dependent variable minus the experimental data like I said this was. So to do this, we're going to make a mesh grid of our two arrays, and what that does is it makes a rectangular grid for our two arrays. So those being our Schmidt grid and our Reynolds grid. And then that will be equal to the mesh grid of our parameters. So Sherwood is 0.6 to 2.5. Width will do 20 data points. Oh. Can't forget numpy. And then our second grid, which is the Reynolds grid, that is 2e to the third and 35e to the third. Width will do 20 points as well. Then next we want to classify our Sherwood grid, and that is basically our correlation right here. But we want to raise the first one to the exponent to get the correct value in that array of W. And that is multiplied by our Reynolds grid raised to our second parameter, and then the Sherwood grid, or the Schmidt grid, my bad, raised to the third parameter. So now that we have these two grids, we want to zip them up, and what the zip function does is it makes a, basically it allows us to combine these two arrays and pairs them together. So for I of Reynolds and I of Schmidt and I of Sherwood, Then we use our zip function. And then we want to fill these with our 3 grids. So the first one being the Reynolds grid. The second one being Schmidt grid. And the third one being our Sherwood grid. And then we want to plot all of these. So figure add trace. And then scatter 3D. With our X being our new variables, IRE, Y as I Schmidt, and Z as I Sherwood. Alright, and then we want to add these in as lines. And we'll make the line color, or the marker color, no, the line color as gray. So let's, nope. Oh, there we go. That was easy to spot. Still something wrong. Oh, there we go. And here we are with our newly plotted lines. And then we want to do that the other way. So we'll just copy and paste this. Then when I'm doing it the other way, we want a set value of Reynolds grid with a varying Schmidt grid. And here we are with our final model prediction, but to get these lines out of the way, we do show legend. Gosh. There we go. And here's our final model prediction for the graph. And that is how you use the mesh grid and zip functions to basically obtain these lines.